Alrighty. So looking at this one here, and we're trying to solve it, which means we need to isolate our trig function first. So what do I need to do first of all? What's our first step going to be? Yep, we're going to divide both sides by 3 square root of 3. So we're going to have that the tangent of x equals 3 over square root of 3. These 3's cancel out. So we're just with 1 over square root of 3. So we're going to look at our unit circle and see if we can figure out where does tangent of x equal 1 over square root of 3. If it helps, you can always remember that tangent of x is sine of x over cosine of x. And that might help us match it up, because we need cosine to have a square root of 3 and sine pretty much to cancel out. So where on our unit circle do we have cosine with a square root of 3 and sine with a 1? Pi over 6. Are there any other places that have those same values? Because sometimes we have more than one. Or am I being tricky and being a jerk right now and asking you a mean question? It's like, it's just the one. I was going to say, because the only other place we have that as far as tangent goes is already into the next period. So tangent we only look at the top half. Everything else would have a sign change. So we're not going to have another one, because it's just going to be pi over 6, and then we add our period. Pi times n, because we're trying to find all possible solutions. So we need to include that pi n, because that gets us all those coterminals. It would give us our 7 pi over 6, because it would be our negative 1/2 over negative square root of 3 over 2. That gets to that 7 pi over 6, because it is coterminal, or it is included in the pi over 6 plus pi. Yes, dear. So if we look at pi over 6, our ordered pair for pi over 6, that is square root of 3 over 2, 1/2. If I take my sine, which is 1/2, and we put it over square root of 3 over 2, those 2's actually cancel out. So you can either think of it as my denominators canceling out, or you can do it as the multiplication of the reciprocal. 1/2 times 2 over square root of 3. It doesn't matter how we simplify it. Either way, the 2's are gone. And we have our 1 over square root of 3. Since on our unit circle, everything is divided by 2 except for those cardinal directions, my 0, pi over 2, pi, those guys, everything else has a 2. So for the most part, those denominators are going to cancel out. So we just got to be really careful. And we're going to go slow, and we're going to take our time, and we're going to do the thing. Okay? So sometimes we're going to throw some weird ones at us. This was not an example of that. They're going to throw some weird ones at us like this. So right now we have sine of 2 theta, which is weird. I don't like the 2 theta. He's kind of gross. So what we're going to do is I'm going to do a substitution just to make my life easier, because I don't have to deal with 2 theta. I would rather deal with x maybe. So I'm going to set x equal to 2 theta. You could do a u, you could do an x, you could do a alpha, you can substitute with whatever the heck you want. So if I set x equal to 2 theta, I know that sine of x is negative 1/2. Where does sine of x equal negative 1/2? What would x equal? Think about your unit circle. Where is sine negative 1/2? It is 7 pi over 6. Is there another one? And 11 pi over 6. So we're going to set these up as their full solutions. So 7 pi over 6 plus 2 pi n and 11 pi over 6 plus 2 pi n. And if we were just asked about x, we'd be done. Woohoo, we're already there. But we were not asked about x, we were asked about theta. So we're going to come back and re-substitute in to put 2 theta equals 7 pi over 6 plus 2 pi n. And 2 theta equals 11 pi over 6 plus 2 pi n. I'm venturing out from this behind it a second. But I don't want 2 theta. I just want theta. So what do I do to get theta myself? Divide by 2. Doesn't matter what hot mess is on the other side. Divide by 2. Right-hand side's a hot mess. But that's okay. We can deal with hot messes. We are super duper skilled like that. So we're going to come over here and we are going to divide this by 2. We're going to divide this by 2. And we're going to divide this by 2. So we're going to get that theta equals 7 pi over 12 plus, and then these 2's cancel. We get pi n. And, so we got to do it to the other side too. That's not how we spell and. There we go. Divide all of these pieces by 2 as well. So we're going to have our theta equals 11 pi over 12 plus pi n. So if we're given something gross in here, inside our trig function, switch it out for something less gross so it's easier to deal with. We can substitute things in if we want to make things easier, as long as we change them back at the end. So we're going to practice that definitely a few more times. Okay, here's our next one. We have sine of 4x equals square root of 2 over 2. So right off the bat, I look at this and I go, ew, I don't want to do 4x. So give me something we can substitute in for the 4x. What do you want to use? What do you want to do to substitute this piece in? Theta, sure. Doesn't matter. There's not a wrong answer there. You can do theta, you could do x. Well, I wouldn't do x because we already have an x. You could do y, you could do a heart, you could do a happy face. It's a variable. It doesn't matter. Need a second? Pieszki. Uh-huh. Okay. Yeah, it's just, right. Okay. Can I talk to you about this later? Because I'm in a class right now. Okay, bye. Yeah. Oh my gosh. Come on, chit chat at me. Okay, so we're going to substitute our theta in. So we've got our sine of theta equals our square root of 2 over 2. So where do we have that sine of theta? What theta is that? Pi over 4. And 3 pi over 4. Both of those have a square root of 2 over 2 as our sine. So we're going to include that coterminal thing. So we're going to also add our 2 pi n and our 2 pi n. But we don't want to know about theta. We need to know about x. So we have to resubstitute back in. So we know that 4x equals pi over 4 plus 2 pi n, and that 4x also equals 3 pi over 4 plus 2 pi n. And what are we going to do to solve for x? Divide by 4, because we're super awesome like that. To all the pieces. Absolutely every piece gets divided by 4. So our x is going to equal what? Pi over what? 16 plus, oh, I don't know where I'm going, pi n over 2. Yeah. So watch out for simplifications. So x equals, and it's very similar over here. We're going to have 3 pi over 16. And again, plus pi over 2n. So set them up as our full rotations and then simplify. I'm going to do one more like this before I give you the next piece. All right. So what's our first instinct here? Subtract 24 is fine. You can absolutely do that. Let's do it. Minus 24 from both sides, totally fine. Gives us 12 cosecant of 2x equals negative 24. Then what can we do? Divide by 12. Divide both sides by 12. We have cosecant of 2x equals negative 2. Yeah, we can do the substitution thing. What do you want to put in place of the 2x? Theta? Totally fine. So now we have cosecant of theta is negative 2. Remember that cosecant is 1 over sine. If that helps, if that step does not help you, you do not have to write that. Like, that's just, I find that helpful. Because if I know that that is 1 over sine, you could flip that and make it sine is negative 1/2. So what thetas do we have that are going to have a cosecant of negative 2? Yes, 7 pi over 6. If this gets you stuck, take it down here to 1 over sine theta and then flip-flop them over. If we know that 1 over sine theta is negative 2, that means sine of theta is 1 over negative 2. So if you get stuck there on these secant and cosecant ones like that, switch them. Take the reciprocal and flip it. It still means the same thing. We just changed which side the reciprocal was on. Either way, we're going to find out that our theta is going to equal 7 pi over 6 was one option, plus 2 pi n. Any place else where we have a sine of negative 1/2? And we have another one at 11 pi over 6 plus 2 pi n. I'm going to give us a little bit more space here. Because we didn't want to know about theta, we wanted to know about x. So we got to come back and take and substitute this piece back in. So we know that we have theta was 2x. So 2x equals 7 pi over 6 plus 2 pi n. And that we have that 2x equals 11 pi over 6 plus 2 pi n. What do we need to do to figure out what our x is? Divide it by 2. On all the pieces. So we're going to have that x equals 7 pi over 12 plus pi n. And we're going to have that x equals 11 pi over 12 plus pi n. Okay, so we wind up with these weird kind of statements for these. When it says find all solutions, we have an infinite number of answers we're going to have here. We're not always going to be asked to find all entire solutions in the entire existence of the universe. Sometimes they're going to limit us to one time around the circle, which is what we're going to talk about next. Because the next thing they're going to ask us to do is to solve on an interval. So they'll give us instructions like this: find all solutions on the interval, and they'll give you an interval, and more times than not, it's going to be from 0 to 2 pi. So just the one time around the circle. More often than not, this is the interval they have us do, which is going to be the one that we're going to practice with. 0 to 2 pi. We treat it exactly like what we've just done, except at the end, instead of putting pi over 6 plus 2 pi n, we're going to figure out exactly which ones they are, and it's going to be what we call a finite list, just a list of the only ones that work. And I have to change the settings, so my screen's going to freak out for just a second. I promise I'll put that back. And it's going to forget my interval that I put up there. I just said my screen's going to freak out. I'll go put it back up there. It's going to forget the interval, but my screen is going to freak out. I got it. I know. I was trying to give you warning. So from 0 to 2 pi, and it just zoomed in and followed my brain, didn't it? No, it didn't. Yay. There we go. So we're finding all solutions on the interval. Okay, so we're going to treat them exactly the same way. We're still going to find them. We're going to still find those rotations. We're still going to calculate it and do it with our pi n or 2 pi n. And just at the end, before we say, all right, here's our answer, we're going to make a list of the things that work. Okay. I still see a bunch of people writing, so I'm going to give you guys a little more time. Totally fine. All right, looks like we have a lot more people in. So let's look at this one. So we're going to solve on the interval. So all of my answers are going to be between 0 and 2 pi. I will not have any answers bigger than 2 pi. So we're just looking at the pure unit circle. And we're going to find when 3 secant squared of theta minus 4 equals 0. So what we want to do is we want to isolate our trig function, just like we've been doing. So what's our instinct here?
Add 4.
Add 4. That's going to give me, that's not a pen. Let's try that again. 3 secant squared of theta equals 4. Divide by 3. So it gives me secant squared of theta equals 4/3. Next thought. What can we do next? Square root. Excellent idea. Square root. So that gives me that secant theta, bless you, equals plus or minus, because whenever we square root both sides, we get a plus or minus. Square root of 4 is 2. Square root of 3 is irrational, so we're going to leave it as square root of 3. So we want to know what thetas have the secant of theta as positive or negative, we don't care, 2 over square root of 3, which is sometimes a little tricky to wrap our brains around or remember until we remember that secant is the same as 1 over cosine. So if 1 over cosine is plus or minus 2 over square root of 3, that is the same thing as saying when is cosine plus or minus square root of 3 over 2. So when we're dealing with the reciprocal functions, it sometimes helps to flip it back over. Pi over 6 is definitely an answer. So let me write them down. So here we got our theta. We've got pi over 6. Where else do we have a positive or negative square root of 3 over 2 for cosine? 5 pi over 6. Where else? 11 pi over 6. And 7 pi over 6. We're not going to put like a plus 2n on here. We're just looking for a finite list. This is our answer. We want just the places. We're making a list. Checking it twice. Okay, so it's a little less, but also a little weird sometimes. Ready for the next one? Sometimes they get a little weirder. So we've got secant squared theta and tangent theta, and we want to know when it equals 1. Ew. Whenever we see something where we have both a squared term and a linear term, we're going to want to try and factor something. So I have a secant squared thing and another trig function. So I have a squared trig function and a non-squared trig function, which means we're going to try and factor something. Yes, Jim? You could do it as cosine over sine. An easier way would be to remember our trig identities. And there is one that relates secant squared with tangent. Because we can rewrite secant squared as 1 plus tangent squared. Because there's a trig identity that was the secant squared equals 1 plus tangent squared. So whenever we see a squared trig function and a not squared trig function at the same time, do your best to get them to be the same trig. So we want them to match. Tangents with tangents, secants with secants, cosines with cosines, whatever. Ideally, they will match. So then what should we do? If we're going to want to try and factor, what should we have it equal? 0. So what are we going to do next? Subtract 1. So I'm going to minus 1 from this side, and I'm going to minus 1 from this side. So it's going to give me tangent squared theta plus tangent of theta equals 0. I'm going to fix that because that looks weird. There we go. So what can we do? Factor out a tangent. It's got a common factor. If it helps, think of it as x squared plus x. We could factor something out. So we can make this be tangent theta times tangent theta plus 1. And it gives us 2 factors, where this is one factor and this is another factor. So just like back in the days of quadratics, way back in the day, where we take each factor and set them equal to 0, it's 100% exactly what we're going to do. We're going to say, all right, when does tangent of theta equal 0? And when does tangent of theta plus 1 equal 0? So what values of theta give us 0 for tangent here? Yeah. Yeah, 0. What the heck was that? Oh my gosh, that was the weirdest 0 ever. My stylus freaked out. It made a square. Where else? Remember, we're looking at the whole unit circle from 0 to 2 pi. Pi over 2 will not give us 0 because pi over 2 is undefined for tangent. Pi. How about for our other side over here? Subtract 1. So we want to know, when does tangent of theta equal -1? That one's a little harder. Whenever tangent equals 1, remember that's when sine and cosine, both pieces cancel out. So sine and cosine have to have the same value. Yeah, it's going to be one of our over 4s. So which one of those are going to give us -1, though? Say it louder. No, 5 pi over 4 is not going to give us that. Because 5 pi over 4, they're both negative. Negative over a negative is going to give us a positive. So 3 pi over 4 will. So 3 pi over 4. Where else is going to give us a negative one? 7 pi over 4. Okay? Because if you think about our unit circle, I'm going to give a sketch here. The only ones where everything's going to cancel out are 45s or pi over 4s. This one, it's positive over a positive, so everything's going to wind up being positive. We need to either have a negative over a positive or a positive over a negative for our tangent to wind up being negative. Okay? Yes. Since we're looking at the whole interval, we have to do that. Otherwise, if you think about it down here, you could also do it as 0 plus pi n. But since we're going the whole circle, I need to get up to 2 pi anyway, so I'm still going to have 0 and pi being the same thing. So you either need to do it this way or look at your whole circle. So it's just slightly different that way. I'm going to say let's be done right there, because that gives us a good kind of intro one for tomorrow before we get into a weird one. Okay, so there's the 7-2 homework detail stuff. Hang on. Thank you. Give me just 1 second. Oh, hang on. It's going to glitch again for us because I think I have missed a quiz date on there. Okay, I'll get it for you. Because we have a... There we go. It's like that one had the wrong quiz date on it. All right, Tia. All right, so you guys have like 3 minutes. I didn't want us to have to try and squeeze another one in there. I know oftentimes I do, but we are in an okay place. We in an okay place.